1379. Let's take a look at 16. Find the equation, the tangent line of the curve, y is root x. So the function in this case is the square root of x. And so we're going to be finding the derivative from the definition. And this uses a little tricky piece of algebra. So I would consider this a hard problem. Remember, looking ahead to your first midterm, have you looked at the study guide? That's on my class website. Tells you how many problems, what each problem is worth, what section they come from. So looking at that, you'll see that there are two problems where you have to find the derivative the hard way, the way that we have been doing it, from the definition of the derivative, which is the limit as h goes to 0 of f of x plus h minus f of x all over h. So there are two of them that you have to work with that definition before you can rest upon your shortcut rules that we are evolving from this definition. One of those two will be easy, one of them will be hard. I consider this root hard because you got to do a little algebra trick. And we'll talk about that algebra trick in a minute. So there's our function, and we want at the point, we'll do it in general, and then we'll find the point at 4, 2. And then they want you to use a graphing calculator and draw the picture. No, you don't have graphing calculators. Yes, on the second midterm, we'll be drawing pictures, but that'll be a whole separate topic. So you're not expected to draw the picture at this point. I guess I could, though. They want you to use a graphing calculator to draw the picture, which we wouldn't in this case, but that's what the graph of root x looks like. You'll learn this for midterm 2. And here we want a point at 4. And of course the square root of 4 is 2. So there's a point. And it wants the equation of the tangent line. Well, the hard part is the slope of the tangent. So here's that tangent line. That's the tangent there in blue. And last time I mentioned how back in high school you should have learned mx plus b, point slope form, intercept form, or maybe point slope form. You know that a line looks like this: y minus y1 is equal to mx minus x1. And this is the point 4, 2. That's our given point x1, y1. So the real problem here, the problem is not the equation of the tangent. The big problem is finding the slope. So m, this is the problem here. M is the slope of the tangent, which is the derivative evaluated at that point. 4, 4, 4. X equals 4. F prime of 4. That's the real guts of this problem. And so let's do that hard work. So the first thing let us do is apply the function. In other words, we want to put the function f in here. And let me just remind you, maybe you don't like my funky boxes, but the point I'm trying to make is when you take f of x plus h, put the whole x plus h into the box. So what you're doing here in blue, that step is the square root of x plus h. And then the green bracket, people usually don't have trouble with the green, they have trouble with the blue, blue minus green. The green is f of x, meaning root x all over h. And again, I keep talking about my funky boxes because you guys make this mistake. Where is my red pen? I save red to highlight mistakes. Here it is. No. What people do is that they do root x plus h. Instead of here in blue. The black is correct, root x plus h. Somehow they pull the h out of the root. And so what I'm saying is that the function is root it. So if it is x plus h, if that's what goes into a box, think of it as a three-letter word. Don't take it apart. It's one thing. Put it in the box. Root quantity x plus h. Okay? And so, as I say, at this point, there is an algebra trick. You did see this in a different context in high school. Let me switch to another color. Purple. Back in high school, did they teach you about rationalizing denominators? In other words, if you had something like 1 over root 7 minus root 5, they considered that improper. You know, after studying math for 60 years, I've never understood why that's improper. I think they declared it improper simply so they could teach you this trick. Because I see nothing wrong with roots in the denominator. But they don't like, the rule is this is improper. They don't like roots in the denominator. And so do you remember they taught you this trick? Do you remember the trick of the conjugate? Something minus something has a conjugate. Replace the negative with a positive. So root 7 plus root 5 is the conjugate of the denominator. And of course, what you do to the denominator, you have to do to the numerator to keep it equal. And so you multiply through by the conjugate. Do you see why that works? Because now in the numerator you have root 7 plus root 5, which is considered proper. I'm not sure why. But do you see in the denominator here, do you see what happens? It's like a minus b times a plus b. Isn't that the difference of squares? A minus b times a plus b becomes a squared minus b squared. A difference of roots, a difference of squares. But now when you square a root, root 7 squared is 7. Root 5 squared is 5. And you end up with root 7 plus root 5 over 2. Does that look familiar? Supposedly somewhere back in high school they taught you about rationalizing the denominators. The only reason I'm mentioning it here is this was supposedly your first exposure to the conjugate. We're going to simplify that guy there by multiplying. It's the same trick. We're rationalizing the numerator, so to speak. multiply through by the conjugate. So let me recopy here. Let me recopy that. I've got the limit as h approaches 0 of root x plus h minus root x all over h. And here is the trick. And so, yeah, either on the first midterm or on the final, I probably will throw this at you, one or the other. You know, as I say, go to my website, look at the study guide. It tells you how many problems, what each problem is worth, what section they're from. And so there are 2 of these that you have to do from the definition. Term after term, I structure the exams the same. Term after term, I just throw in new functions. So at this point, I can't tell you for sure. Is this going to be on midterm 1? Is it going to be on the final? I don't know at this point. Because when I go to make up your exam, then I just make up problems to fit the outline. So one way or another, you're going to have to do this. The conjugate. So if this is minus, the conjugate is plus. Were this plus, then the conjugate would be minus, which wouldn't happen in this context, but just conjugate means replace the plus with a minus or a minus with a plus, whichever way. Okay, do you see why the trick works? Do you see why the trick works? Here in the denominator, nothing happens. We've got h times the conjugate. But here in the numerator, look what happens. You have a minus b times a plus b. Doesn't that sound familiar? If you have a plus b times a minus b, don't you have a difference of squares? Isn't that a squared minus b squared? And look, I know in a sense you guys have got more work to do than usual. 2 years of distance learning with COVID. We math teachers have discovered has caused a big gap in your math education. Math is really not something you can do by distance learning. You got to stare somebody in the eyeballs to get it across. So all math teachers talk about this. And in a sense, you guys have got it doubly hard because I'm expecting you to remember these old rules. Even though you had a 2-year hiatus, you know, you got to pick up your algebra. And so, a minus b times a plus b, different squares. So that's root x plus h squared minus root x squared. Are we okay? You're applying that rule here. And now, doesn't that get nice? Because you're squaring a root. That's just x plus h. You're squaring a root, which is just x, over h root x plus h plus root x. And now you see nice subtraction. X subtract x. So you're just left with an h in the numerator. So this is the limit as h approaches 0 of. The numerator only has an h in it. The denominator has an h root x plus h plus root x. And here's where you invoke the idea of limit. The whole idea of limits is getting around the difficulty of division by 0. You can't divide by 0. 0 over 0 is meaningless, which is the problem with instantaneous speed. Speed is distance over time, and in an instant, time has gone to 0. So how does limit help us get around this problem? Because H is only getting close to 0. It doesn't equal 0. H is tiny. And as long as it's tiny, because it's not 0, you may cancel factors. If H is a tiny positive number, now it is legal. You don't have 0 over 0. Cancel common factors. And in the numerator, you're left with 1. And in the denominator, you have the sum of the roots. Are you okay that that is 1 and not 0? Some people make this mistake. If you've got A over A, I'll make it AB. If you've got A over AB, you may cancel the A's, you're canceling a common factor, and you're left with 1 over B. Okay? I grabbed my red pen. This is the mistake, don't do this. They'll say 0 over B, no. A is the same as A times 1, right? A is the same as A times 1, which is why you have a 1 there. People mistakenly put a 0 there. Okay, and now, H is a tiny number. So this is getting close to root x plus root x is to root x. If you wish, you could think this way. Now you don't have division by 0. You've eliminated the problem of division by 0. So now it's legal to plug in 0 for H, because this is just getting closer and closer to root x. So you end up with root x times root x, plus, let's copy it. Root x plus root x gives you 1 over 2 root x. And so that's been the hard part. And we can go back and finish off the tangent line here. This has been the hard part. So f prime at 4, plug in 4. 1 over 2 root x, but x is 4. Root 4 is 2 times 2 is 4. So what that means is, here's our line. Y minus 2 equals, this is m. M is a half. X minus 4. So the hard part of this problem was coming up with m. Once you have m, the equation of the line is easy because you know the point of tangency. Take the point of tangency as the known point on the line. Plug in 2, 4 for x1, y1, and 1/4 for m. How are you doing? Anything you want to ask? Yeah.
Wait, where do you get the 1/2 from for the slope?
Thank you, G.
Is that supposed to be 1/4?
Yeah, thank you, G. Cut my head in and start thinking right. 1 over 4. I'm sorry. Thank you.
Where did the H go? Like for the denominator?
Yeah. How do we get from here to here? How do we get from here to here? There are 2 ways you can think about it, and use whatever way speaks to you. Remember, H is tiny. It's getting closer and closer and closer to 0. So that means the x plus h is going to 0. So in the limit, it's getting closer and closer just to root x. That's one way to think about it. Here's another way to think about it. You see, the reason we couldn't plug h in here as 0 is we have 0 over 0, which is not legal. So here we couldn't plug h in as 0. Here we could because there's no division by 0. The h is tucked inside of this here root. And so now it is legal to plug 0 in for h.
Okay.
So it was not legal here, because you can't divide by 0, but it is legal here because you aren't dividing by 0. Whatever explanation grips you.
Alright, thank you.
Okay? Are we okay? So please ask questions. Not that I've taught up at stores recently, but I'm told that this business calc up in stores has like 250 people in the lecture hall. Huge.
One class had just I think 30 people though in the Monteith building. One class.
I mean, 30 is a good number.
Yeah.
Yeah. I mean, I haven't been up there recently, but when this class is taught with 250 people, there's simply no way you can ask questions because you're in a great big lecture hall. Also, when the classes get too small, like not this summer, but last summer, in account 3, I had 4 people. When it gets too small, then people are too self-conscious and won't ask questions. 30 is a nice size because, you know, somehow you're not shy then about asking questions. So please ask questions. Questions are important. I know we've got number 24 here, but before number 24, I want us to pull together everything we've been learning because this comes together. 4.1 is bringing together all of the rules that we've been learning. And let me do that now. Really, I'm not saying much new. And in fact, this number 16 that we just did is going to be a good case in point. So, .1 is really just a summary of the stuff that we've been doing. A couple of times now, we've found the derivative of x squared. We've done this in a couple problems. We've used the long definition, limit h goes to 0. We've done this a couple of times. And we've already seen that if you got x squared, the derivative is 2x. And we had one problem that did this, x cubed. And I said you had to remember how to expand a cube in that context. And in that context, you saw that it was the second term of the expansion that gave you the derivative. We saw that derivative was 3x squared. And what we just did root x. And let me remind you that if you wrote root x in power form, it'd be x to the 1/2 power. Remember, fractional powers mean roots. So x to the 1/2 is root x. And we just saw, this is what we just did, that this was 1/2 root x. Can I write that this way? The 1/2 is a half. And I have root x in the denominator. Do you remember how to write that in power form? Negative 1/2, is that okay? Negative power means reciprocal. Fractional power means root. Are we okay with that? I know in the first week we reviewed these. Power rules. Y'all got to be on board with this. X to the 1/2 means root x. X to the negative 1 means 1 over x. Fractional powers mean roots. Negative power means reciprocal. So if you mix it up, if you got x to the negative 1/2, are you okay? The negative is reciprocal. The half means root. So that's why you've got them both there. Okay. So if you look at these three examples we've done, the derivative of x squared is 2x. The derivative of x cubed is 3x squared. The derivative of root x is 1 over 2 root x. There is a pattern here. And in the engineering calculus 1131, we use the binomial theorem to prove this pattern. Well, in here we don't assume you remember the binomial theorem. But let's take a look at this pattern. I think you can induct this pattern. What if we have x to the n? Do you see the pattern? X squared went to 2x, which is 2x to the first power. X cubed went to 3x squared. Doesn't it look like that? The power n comes down in front as a coefficient. And the new power is 1 less. That's the pattern we've been picking up. Does it make sense? X squared, the 2 comes down in front, and the new power is 1 less. X cubed, 3 comes down in front, and the new power is 1 less. Check it here with f as root x, or x to 1/2. According to my pattern, let's check it out. The 1/2 comes down in front as a coefficient. The new power is 1/2. 1/2 subtract 1. Are you okay with your fractions? 1/2 subtract 1 is negative 1/2. Which is what we said. Okay? So here is what 4.1 is all about. And so now after 4.1, you no longer have to use that limit definition thing for polynomials. You already know what happens. So this is a shortcut rule. Which we call the power rule. Let's do another example. Here, this will fit. What if your function is just a constant, let's say 7? That fits our rule. Because if your function is just a constant 7, the power of x is 0, right? Anything to the 0 power is 1. Anything to the 0 power is 1. And what does our rule say? F prime would be 7 times 0. And anything times 0 is 0. And so we've already seen this, that the derivative of a constant is 0. We did a couple examples of that. The derivative of a constant is 0. Now there's one other shortcut rule that we've seen. I believe we did this problem. Instead of x squared, I believe it was 5x squared. I believe we did that problem. And what we saw was the answer was 5 times 2x or 10x. So, the x squared, the derivative became 2x, and the coefficient 5 just stayed. That's the rule. Coefficients stay. So coefficient, that means a number multiplied, a factor. Coefficients stay. And so now, we did a line. Here's another example we did. We did the example of a line. F of x was mx plus b. And we found that the derivative was, well, b is just a constant, its derivative is 0. But mx, the derivative of x is just 1, and m is a coefficient that stays. So m is a coefficient that stays. The power comes down in front, and the new power is 1 less. But of course, x to the 0 power, anything to the 0 power is 1. So we had done that example, and it fits our rules. So there are really 3 shortcuts here. Here's the power rule, and then coefficients stay. That's sort of a shortcut. And the derivative comes to 0, that's a shortcut. So what we're doing here in chapter 4 is we're gathering together these shortcuts that we've been illustrating in chapter 3. And what this means now is you can find the derivative of any polynomial. You don't have to do the limit stuff. Now, you know the derivative of any polynomial. So let's say that f of x is 7x to the 4th minus 3x cubed plus 13x squared minus 141x plus 17. Just pull out any random polynomial. You know the derivative. Let's do it. So 7 is a coefficient, it stays. X to the 4th, the 4 comes down in front as a coefficient, the new power of x is 1 less. 3, that is a coefficient which stays. The old power of 3 comes down in front as a new coefficient, and the new power of x is 1 less. 13 is a coefficient, it stays. The old power becomes a new coefficient, the new power is 1 less. And here, 141, that's coefficient, it stays. The derivative of x is just 1, or 1 comes down in front, the new power of x is 0. And then 17 is a constant, meaning it doesn't have an x with it, just plain constant, constant 0. So if you want to clean this up, 28x cubed minus 9x squared plus 26x minus 141. There's your derivative at sight. And let me just say, by way of encouragement, why are you doing this stuff? If you remember your macro, profit is maximized when marginal profit is equal to 0. From a calculus point of view, that's a one-liner. You take the derivative, you set it equal to 0, and you find out what your maximum profit is. So as I've been saying, a lot of what sounds like deep economics is really kind of easy math. And I'm just, oh, yeah. There are two other shortcut rules. And here in 4.1, did they just give them to you, or did they make the pretense of proving it? Oh. Right. They didn't prove it, they simply put it in the calculator and said, looky, looky. And for the log, it says, the complete proof can be found in the enrichment subsection. Okay. So, here in 4.1, there are a couple other shortcut rules, and they don't prove these to you. They just give these at face value. You remember that we have already talked about how two particular functions are of important economic value, e to the x and log x. So back in the first week, didn't we talk about compounding interest continually and then solving an exponential equation? So e to the x and log x, these are important functions with economic applications. And so here they just give you the derivatives. These derivatives are, they're simple, but they're kind of hard to prove. And the book doesn't offer proof. Maybe later, if I have time, I'll wave my hands at it. But e to the x has a particularly nice derivative. And in fact, this is where the number e actually comes from. E to the x is its own derivative. And e is the only number that will do that. You know, we talked about 10 to the x, talked about 2 to the x. We could talk about an exponential function to any base, but only e will do that. E to the x is its own derivative. And that's where this funny number e comes from. So remember, like pi is an irrational number, means it has an infinite decimal expansion that doesn't repeat. E is this 2.71828. Blah, blah, blah. And where does that funny number e come from, 2.71828? It comes from this property. It's the only base that is its own derivative. And now I should tell you what the derivative of the log is. It's particularly nice. Simply 1 over x. Simply 1 over x. Okay, so all of that now you can do for 1. And so I've got time to okay. Problem 24. It draws this picture for you. Got a vertical asymptote at the x-axis, closed out here, comes down to a point, comes up to a closed dot, and then an open dot, and then G takes off. Okay. And they're asking, for what values of x does G prime not exist? Okay. Where does the derivative G prime not exist? So remember, G prime is the slope of the tangent. Where does this graph not have a tangent? Well, you see at the origin, this thing is asymptotic. It's blowing up on the left-hand side. And so there's no tangent there. Now, where it comes to a point, later on when we talk about graphing functions, where it comes to a point like that is called a cusp. So is that at 1? Yeah. There's a cusp at 1, and so there's no f prime at 1. Because you see it's ambiguous. Math hates ambiguity. You might say, well, a tangent intersects the graph just in one point. Yeah, but look. There's a line that intersects at only one point. There's a line that intersects at one point. Which one is your tangent? It's ambiguous. So math does not have ambiguous things. Also here, was that at 2? Here at 2, there's a problem. Because you got a gap. Again, it's ambiguous. Maybe on the left, it looks like this, but on the right, it looks like that. So again, it's ambiguous. Nothing which is ambiguous in math exists, which is why mathematicians make very bad psychologists. Every one of you in here both loves and hates your mother. Therefore, your mother doesn't exist mathematically. All right? Mathematicians make very bad psychologists because math does not tolerate ambiguity. Okay, so with that, I think you'll find, and I've only allowed one day for 4.1 because I think 4.1 is pretty cut and dry. We'll look at 4.1 on Wednesday. See you Wednesday.